use the fundamental theorem of calculus to find dy dx. And here we have a big definite integral. We have the definite integral from the square root of x to 3x of t squared times sine of t squared plus 1 dt. Now, we have to be mindful here. Notice that we have an x in both bounds. So we're going to need to separate this definite integral into two pieces before we can even apply the fundamental theorem. So let's let some arbitrary a value here live within the open interval of those bounds. So we'll say that a lives somewhere in between the square root of x and 3x. So by the additivity property, we can separate this definite integral into two pieces. So by the additivity property, we're going to take the definite integral of the square root of x to 3x of t squared times sine of t squared plus 1 dt. And we're going to rewrite this as the definite integral from the square root of x to a of t squared times sine of t squared plus 1 dt. And we'll add the definite integral from a to 3x of t squared times sine of t squared plus 1 dt. So now we have separated our definite integral here into two pieces, and we're almost ready to apply the fundamental theorem. This second integral is in great shape. We've got the constant bound in the lower bound and the x bound above. But looking at our the first integral here, right, notice that x is in the bottom bound, or is the lower limit of integration. And the constant is the upper bound. So we need to flip this. And how can we do this? Well, let's apply the order of integration property. So by the order of integration, we can rewrite this definite integral as follows. So this is going to be equal to minus the definite integral from a to the square root of x of t squared times sine of t squared plus 1 dt plus the definite integral from a to 3x of t squared times sine of t squared plus 1 dt. And so now both definite integrals are in good shape. We have the constant bounds in the lower bounds with the x bounds above. And so we're ready to apply the fundamental theorem. So to get us ready, let's say that this is our function y. And to apply the fundamental theorem of calculus, we now need to differentiate both sides with respect to x. So by the fundamental theorem, we are taking the d dx of both sides. So let's do this in the step above. So taking the d dx, taking the derivative of both sides with respect to x. And we'll think about this in two pieces here. I'm distributing the d dx to both integrals, both definite integrals. So the fundamental theorem of calculus says, we're going to take this, well, it says that the derivative of the definite integral gives us the original function. And let's show that. So we're going to take these upper bounds and plug them into the function to replace the x, or to replace the t with that upper bound. Just don't forget to multiply by the derivative of your upper bound. And we'll do that twice here. So again, we're replacing the t of the integrand with that upper bound and multiplying by the derivative. So this will leave us with the derivative of y with respect to x is equal to minus the square root of x squared multiplied by sine of the square root of x squared plus 1. And we're multiplying by the derivative of that upper bound. So we have the d dx of the square root of x, which I'll write as x to the 1/2. And don't forget that second definite integral. So this will be plus 3x squared multiplied by sine of 3x squared plus 1 multiplied by the derivative of the upper bound. And we can simplify. So we see we have the square root of x, and the square will cancel twice here. So we can rewrite this as being equal to, we have minus x times sine of x plus 1 multiplied by the derivative of the square root of x. So that's going to be 1/2 times x to the negative 1/2 plus, we have 3x squared, so that's going to be 9x squared multiplied by sine of 9x squared plus 1 multiplied by the derivative of 3x, which is 3. And we can simplify some more. Let's see, we can rewrite this first term as minus x times sine of x plus 1 all over 2 times x to the positive 1/2 plus, we have 27x squared multiplied by sine of 9x squared plus 1. And that 27 came from multiplying 9 and 3. And we can simplify one more time. We see that we have an x to the first in the numerator and an x to the 1/2 in the denominator. So a little algebra here. We can combine those together. That's x to the first minus 1/2, which leaves us with x to the positive 1/2, or the square root of x. So our very beautiful, very large final answer by the fundamental theorem of calculus, the derivative of y with respect to x is minus the square root of x times sine of x plus 1 all over 2 plus 27x squared times sine of 9x squared plus 1. And there you have it, our beautiful final answer. And so remember, we could always double check our answers here by first evaluating the definite integral and then differentiating the results. It just becomes a little hard to do that when you have integrands that look like this. So that's when the fundamental theorem of calculus sure does come in handy.